Hi everyone, Martin here.
And welcome to the Inner Loop.
Welcome to the Inner Loop. Welcome to the Inner Loop. Welcome to the Inner Loop. Welcome to the Inner Loop.
On
In this episode, we're going to look at multiplexing.
Possibly the D2A as well.
And probably a few other things.
Let's have a look at the pinout on the Pico. The PicoDrone has never really been designed. I decided that I wanted a 14-bit D2A, and in making that I've used up 14 of the pins. These three here have been used by the A to D, which I use for the pots. So that only leaves 9 pins. With these 9 pins, I have to control 14 switches for the oscillators, 2 select keys, and 4 LEDs. So let's have a look at how I managed to achieve that.
I'll try and explain this 4 into 1, and then we can work out from 4 into 1 how we go 16 into 8. My approach is to use time domain multiplexing. So what that means is we have 4 lines, and these will alternate being high. So these wires are oscillating, going round and round. If I was to then join them all together via my switches, like this, and then measure the voltage here, or is this true or false? If I know the time is here, so this is time 1, time 2, time 3, time 4. If I know it's time 1 and this is true, then I know that that switch is closed. If it's time 2 and it's not true, I know that this switch is open because this is where the electricity is going. If it's time 3 and it's true, then I know that this switch is closed. And then if it's time 4 and it's true, then I know that that switch is closed. So by splitting out by time, I've got 1, 2, 3, 4 outputs here. I've managed to make it into one input. So actually that's not very good, because I've used up 5 pins to measure 4 things. But because we've already got this, if I was to have another set of pins here, and here, and here, and another set of switches, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and connect them to the same, essentially connect them to the same place, and measure these pins. Now I've got 4 pins in, 4 pins out, that's 8 pins, but I'm now measuring my full 16 switches. Because if I measure this pin at time 1, and that's closed, then this pin will be high. If this one's closed, this will be high. So by doing this time domain multiplexing, the number of pins that I need is essentially 4 by 4, which gives me 16 switches. There is a complexity here though, because it isn't just as simple as wiring this like this. Because if you look in the latest Look Mum No Computer video, you'll actually see he had exactly the same problem. So here's the wrap. If we have our timing pin here, and we have our measurement pin here, we're going to have 4 switches. 1, 2, 3. So these timing pins will be changing in value between 1, 0, 0, 0, and then this one will be 1 by the whatever. Ignore that. If I press this switch down and this switch down at the same time, then this is essentially going to short circuit the Pico, because one pin's going to be 1, one's going to be 0. So the way around that is to add in here a diode. And these diodes will prevent the current from flowing back to what wants to be 0. And in that way, if any one of these switches are pressed, so if this one's pressed, this is plus, the plus won't, if this one's plus, the plus won't be able to get back to any of the other ones, which means we only ever measure the one that's 1. So essentially, what we're creating here is an OR gate. If any one of these is 1, this will be 1. So that solves with 4 of these. You have 4 of these lines, 4 of these, 16 switches with 8 wires. That leaves 1 pin. With that 1 pin, I have to drive 4 LEDs. But we already know that we've got 4 lines, which the driver lines, 1, 2, 3, 4. So driving an LED is as simple as connecting the LED and I was even extremely stingy and I just had one current limiting resistor because only ever one LED is going to be on at a time. But that isn't actually the full story because instead of going to there, the current limiting resistor actually goes to our final current limiting resistor goes to our final LED pin. Doesn't go there. By going to the LED pin, if the LED pin is 0, then the current can flow through the LED. So actually, to turn an LED on, we need to put this line to 0. But we can do this again in the time domain. When this is on, if we're here, put this pin to 0. So if we know the driver pin is 1, we put the LED pin to 0, and the LED will come on. The LEDs will only be quarter bright. So we couldn't do this over 100 LEDs to really increase the multiplexing because they're going to get too dim. But over 4, I think I find the LEDs are really bright enough. I used quite a small resistor here, it was 100 ohms, I think. So that's how I solved the 16 switches and 4 LEDs with 9 wires. This was 1 and the 9. Because this was already in existence, this was already running. And it occurred to me that I could even use this process for the 3 pots. And maybe on the next version of the PicoDrone, it will have 4 pots. And I can use only 1 analog to digital input, and that gives me 2 more pins for something else. As I mentioned at the end of the last video, the PiPico's got 2 cores. The top core is doing all of this work. It's doing actually creating the oscillations and that stuff. The bottom core is running all of this stuff. And it's this that we're looking at. Well, that's a bit stressful. How on earth do I run 2 programs at once? Because I've got one bit of code. I've got to do 2 things at once on the Pico. But fortunately, the SDK is really well built. So it's very easy. See here, this in my main program, beginning my main program, what I do is I run multi-core launch, core 1, knobs thread. So what that's going to do is kick off a separate thread on the other core of the CPU or the other actual CPU to run the knobs thread. So let's look at knobs thread and see what that does. Here it is, knobs thread. Let's get to the multiplexing part, which is what we're really talking about. First thing we need to think about is the multiplexing of the switches. So I've got a variable called SM, which is the switch variable, which increments every time we go around this knobs thread. The knobs thread is very similar to the other thread in that it has the weight at the top, the delay and weighted. So it runs at approximately the same speed as the main thread, like 48,000 sample rates per second. It's important for knobs thread to run
a very strict timing because it's responsible for the ADSR. And if the code was to go faster or slower, then the ADSR on the notes would be no good. Anyway, back to the switches. I've got a number of pins defined, S1, S2, S3, S4. These are the input pins, those 4 input pins for the switches. And I've got 4 output pins defined, D1, D2, D3, D4. Those are the driver pins, so those are the 4 pins that do the driving. The switches comes around with a variable SM, which has a value of 0 to 3. When it gets to 3, see here it goes back to -1, so it gets incremented and goes to 0 again. So each time we come around the loop, we'll be looking at one version of this. When we first come in, D1 will be set to 1. So driver 1 is set to 1, and then we measure switches 0, 4, 8 and 12 from S1, S2, S3, S4. Then driver 1 gets set to 0, and driver 2 gets set to 1, which will be ready for the next time we come in here and we start measuring switches 1, 5, 9, 13. Again, we're getting the same switch 1, switch 2, switch 3, switch 4, but we've changed the driver, so we've changed the switches that we're checking. We'll come around again, and then we measure switch 2, 6, 10, 14. So this process, after 4 loops, has updated the array for switches for all 16 switches. What we do with the LEDs is a little bit subtle, but we put the pin driver 1, which is the driver for LED 0, on when we're in case 3. The reason being that I want to set the driver pins at the end ready for the next one. So in order to turn on or off or whatever LED 0 wants, we set LED 0 at the end of case 3, and then we'll set LED 1 at the end of case 0. This is when it lines up, essentially, when we put that and put that. This will determine LED 1, but it actually happens during case 0.
That was a bit of a whistle-stop tour of the code. I think it's actually quite hard to explain without really drawing lots of diagrams. I wanted to show how sparse the number of wires actually are on the back of the PicoDrone, considering there's 16 switches and 4 LEDs. The diodes that I was talking about are actually hidden away here under hidden away here in pairs of 4, hidden away under here in shrink wrap. And that's where the 4 control LEDs are here. There's quite a lot of other multiplexing that actually occurs in the PicoDrone. The 3 knobs, for example, each time you move this LED here around a function, it actually changes the function of these knobs. So these knobs themselves are actually multiplexed, and that's why if I select something, I have to press for it to flash, because this will now activate these knobs for this function. So if I press here, this is flashing. This now changes the function of this knob. I'll change it again. This is now changing the timing on the delay. In this mode, this affects the ADSR, the attack time. In this mode, it affects the octave.
So there's the multiplexing for the functionality of these two simple switches, and also of the pots as well.
I made a couple of major tweaks to the D2A code. It seemed so simple in the last episode to discuss it, but I realised that I'd made a mistake here and set this value as an unsigned integer, which would basically lose all the negative values for the D2A. So I fixed that. Also, before, I was setting the pins based on an ANDing of the pin values. But what occurred to me would be happening is each pin would be changing at a subtly different time. And if it's changing at a different time, then the values that the D2A is making would be not necessarily consistent for a very short period of time whilst this process ran. But I found the Pico can actually do a put mask. So you can say to the pins all at once, go and be this value. And I think it's really changed the sound quite dramatically on the PicoDrone and driven me forwards again.
Thanks very much for watching. That's been a bit of a whistle-stop tour through the whole multiplexing of the keys, the LEDs, the select switches and stuff, and the pots. So what really all remains now is just a general overview of the sequencer and the ADSR and the LFO and how those things all fit together. So thank you very much for watching, and I'll catch you next time on the Inner Loop.